Hello, everybody. So in the previous lecture, we introduced the notion of spectrum for an element of an associative algebra. So let's recall the definition. Suppose that A is a unital algebra. And let's recall that all our algebras are assumed to be associative. And over the complex numbers. I'd like to stress once again that this assumption, the assumption that we work over the complex numbers, is quite essential. We will see today that it will be essential that it is algebraically closed, and also we will extensively use some tools from complex analysis, which are not available in the context of real numbers. We denote by A cross the set of all invertible elements in our algebra. This is the multiplicative group of A. And if we have an element little a in our algebra, we define the spectrum of this element to be the set of all complex numbers lambda, such that A minus lambda is not invertible. This is the spectrum of A. Well, we considered some concrete examples of how this notion looks like for some concrete algebras. And today let's discuss some simple algebraic properties of the spectrum. So to begin with, we have the following simple proposition. Suppose that we have a unital algebra homomorphism from A to B. A and B are unital algebras, and phi is a unital homomorphism. That is a homomorphism which takes the identity of A to the identity of B. And first of all, I claim that phi takes invertibles to invertibles. We have the following inclusion. Second, phi reduces the spectrum in the sense that the spectrum of phi of A is contained in the spectrum of A. And this holds for each element of the algebra A. And finally, property 3. So let's look at the following condition. Phi takes non-invertibles of A to non-invertibles of B. Of course, I don't claim that this condition always holds, but I claim that this condition holds precisely when phi preserves the spectrum. That is, we have the following identity for each element of A. Well, the proof is a simple algebraic exercise. So property 1 is well known and is almost immediate. Property 2 readily follows from property 1 and from the definition of the spectrum. Oh, I forgot to... where's the recording? Oh, here it is. Recording in progress. Sorry, I'll repeat once again very briefly because I've just turned on the recording. This is the definition of the spectrum, which was given at the previous lecture. And now we'll discuss this simple proposition which describes the behavior of the spectrum under unital homomorphisms. So if A and B are unital algebras, and phi is a unital homomorphism from A to B, that it is a homomorphism which takes the identity of A to the identity of B. Then first of all, it takes invertibles to invertibles. Second, it reduces the spectrum in the sense that we have the following inclusion. And finally, phi takes non-invertibles to non-invertibles if and only if it preserves the spectrum. So the proof is a simple exercise. The first part is absolutely elementary, and is well known. Part 2 follows from part 1 and from the definition of the spectrum. And the equivalence in part 3 is also proved in about the same way. Here is a useful corollary of this result. Suppose that A is a unit of algebra, and suppose that B is a subalgebra, that is a subring which is simultaneously a vector subspace. And suppose also that they have a common identity, that is, the identity of A belongs to B. Then, for each element little b in B, the following inclusion holds. The spectrum of B calculated with respect to the bigger algebra A is contained in the spectrum of the same element calculated with respect to the smaller algebra B. So the spectrum is, the algebra is bigger, the spectrum is smaller. This is the general rule. Well, this is immediate from part 2, so we simply apply the fact that homomorphisms reduce the spectrum to the inclusion map of B into A. So the inclusion of B into A is an algebra, is a unit of algebra homomorphism, and we have this inclusion. Sometimes, in some concrete cases, this inclusion is an equality, and there is a special terminology for this. Let's give the following definition. We say that B is spectrally invariant. Spectrally invariant in A if this inclusion is an equality. So the spectrum of B doesn't depend on the choice of a subalgebra which contains this element for each little b in the subalgebra. Well, if we apply now part 3 of this proposition, part 3 of this proposition to the inclusion map of B into A, then we see that this property holds if and only if we have the following inclusion. The non-invertibles of B are contained in the non-invertibles of A. Or equivalently, this means that we have the following quality, which means that you have an element of B which is invertible in A, then this element is invertible already in B. That is, the inverse element belongs to the same subalgebra B. Well, let's look at some examples of such algebras, subalgebras, and some counterexamples. First of all, well, if you take any topological space X, then the algebra of continuous functions on X is spectrally invariant in the algebra of all complex valued functions on X. Here, X is any topological space. Well, this is more or less clear because a function in this algebra or in this algebra is an invertible element, even only if it doesn't vanish. It is nowhere vanishing. And so this criterion holds in this algebra and also in this algebra. And so we have this equality. So the subalgebra is spectrally invariant. Second, even now we have a Banach space. Suppose that E is a Banach space. Then the algebra of bounded linear operators on E is spectrally invariant in the algebra of all linear operators on E. This is not obvious from the definition. Actually, this is a corollary of not a corollary, but almost an equivalent form of the inverse mapping theorem, which was discussed at the previous lecture. This follows from the inverse mapping theorem. Let's recall that the theorem states that if we have a bijective bounded linear operators, a bijective bounded linear operator between Banach spaces, then it is a topological isomorphism. That is, the inverse operator is also bounded. But this means exactly that we have this equality. So this subalgebra is spectrally invariant. By the way, for normed spaces, this is not true. It is essential here that E is a Banach space. And now a non-example. If we take any infinite set, X, then the algebra little L infinity of X, of all bounded functions on X, is not spectrally invariant in the algebra of all functions on X. Is not spectrally invariant. And these subalgebras are spectrally invariant. And this one is not. Why is it so? Well, we have already discussed at the previous lecture that a function, a bounded function on X, is an invertible element in this algebra, even only if it is bounded away from 0. That is, 0 is not in the closure of the range. And this is different from the invertibility criterion here. So if X is an infinite set, we can always easily construct a function which is nowhere vanishing, but which is not bounded away from 0. And this shows that this subalgebra is not spectrally invariant. Our next result, or the next important algebraic property of the spectrum, is the so-called polynomial spectral mapping theorem. Suppose that A is a unital algebra, and little a is an element in our algebra. And let's take a polynomial, a complex polynomial f of one variable. Well, we can always consider the element f of a. A is a unital algebra, so we can substitute little a into our polynomial and get another element of the same algebra. So what is the spectrum of this element? Well, the answer is given by the following nice and easy to remember formula. This is f of sigma of a. That is the image of the spectrum under f. So in my view, this is very elegant, and we will see that this is quite useful. And this formula holds almost everywhere. More exactly, it holds unless the spectrum is empty. And f is a constant. It's more or less immediate that in this case the formula fails because the right-hand side will be empty. But the left-hand side is the spectrum of a constant. And the spectrum of a constant is essentially this constant multiplied by the identity. So in this case, the formula fails, but this is the only case. In all other cases, the formula is true. By the way, this result, the polynomial spectral mapping theorem, has many useful analytic counterparts. For example, if our algebra is not just an algebra, but is a Banach algebra, we'll introduce Banach algebras a bit later today. So if A is a Banach algebra, then it turns out that this expression f of a makes sense not only for polynomials, but also for each holomorphic function on the neighborhood of the spectrum. And this formula still holds. Also, another example, if little a is not just an element of a Banach algebra, but is a bounded self-adjoint operator on the Hilbert space, or more generally, a bounded normal operator on the Hilbert space, then the expression f of a makes sense for each continuous function on the spectrum. And the formula still holds. This result will be proved in the next course on operator theory next spring. Okay, now to prove the polynomial spectral mapping theorem, we need a couple of lemmas. Lemma 1. I claim that an element of our algebra A is invertible, even only if it is left invertible and right invertible. That is, if there are two elements, AL and AR, in our algebra, such that AL is a left inverse of A and AR is a right inverse. And lemma 2, suppose that we have finitely many commuting elements in our algebra, A1 to AN. Essential that they commute. Then I claim that their product is invertible. The product is invertible, even only if all of them are invertible. Well, of course, the right to left implication holds for each family of elements, not necessarily commuting. But the left-to-right implication, to prove the left-to-right implication, we must use essentially the assumption that they commute. The proofs of lemma 1 and lemma 2 are useful exercises for you. They're quite easy. Actually, we need lemma 1 to prove lemma 2. And in what follows, we will use only lemma 2. Let's now prove the polynomial spectral mapping theorem. First of all, we may assume from the very beginning that f is not a constant. That is, the degree of f is positive. Because if the degree of f is 1, is 0 if this is a constant, then we have two possibilities. If the spectrum is empty, then the formula is not true. So this is a part of the statement. And if f is a constant and the spectrum is not empty, then the formula is trivial. So we may assume from the very beginning that the degree is positive. Okay, now we take an arbitrary complex number lambda. We consider the polynomial f minus lambda. And we decompose it in the following way by using the fact that the field of complex numbers is algebraically closed. Here C is a non-zero constant. Of course, I don't claim that lambda 1 to lambda n are all different. There can be multiple roots, but this is not essential for the proof. Lambda 1 to lambda n are precisely the zeros of the polynomial f minus lambda, or equivalently, this set is the pre-image of lambda under f. This is immediate from this formula. And let's now substitute our element little a to this formula. So we have the following equality. And now we apply lemma 2. We apply lemma 2. Lemma 2 implies that lambda belongs to the spectrum of f of a, even only if this element is not invertible. So now, since these elements are obviously commuting, we see that this element is not invertible, even only if at least one of these factors is not invertible. So equivalently, our lemma states that the product is not invertible, even only if at least one of them is not invertible. So this holds even only if a minus lambda I is not invertible for some I. This follows from lemma 2. Or equivalently that lambda I belongs to the spectrum of A for some I. If we now recall that the set lambda 1 to lambda n is the preimage of lambda, we see that this happens even only if the intersection of the spectrum with f, the preimage of lambda, is non-empty. Or equivalently, this means that lambda belongs to f of sigma of a. And this completes the proof. Okay, now another closely related result is the following proposition. Again, we assume that A is a unital algebra. And suppose that little a is an invertible element of this algebra. Then the spectrum of the inverse element is given by the following formula. So in some sense, this is the inverse of the spectrum of A. That is, we consider all points of the spectrum and we calculate their inverses. To prove this result, we take an arbitrary complex number mu. And by the way, we may assume that mu is not 0 for the simple reason that 0 is not here, obviously, because this element is invertible. So 0 is not here, and also 0 is not here. So we can consider only non-zero complex numbers. And we look at the following element, A inverse minus mu. So this element is not invertible. Well, maybe it will be more convenient to prove, to look at the situation where it is invertible. So this, well, maybe let me write this more explicitly. So mu is not in the spectrum of A inverse, even only if A inverse minus mu is invertible. But we can now multiply this element by A, and this is equivalent to say that the product of A and this element is invertible. Here we use the simple fact that the product of two invertibles is invertible, and the product of an invertible element and a non-invertible element is not invertible. So we have this equivalence. What is this? This is just 1 minus mu A is invertible. Now we divide this by minus mu, and we see that this is equivalent to say that A minus mu inverse 1 is invertible. But this means exactly that mu inverse is not in the spectrum of A. Mu is not in the spectrum of A. Mu inverse is not in the spectrum of A. Or equivalently, this means that mu is not in this set, in the right-hand side of this equality. And this completes the proof. By the way, these two results, the polynomial spectral mapping theorem and this formula for the spectrum of the inverse element, are special cases of a slightly more general result, namely the spectral mapping theorem for rational functions. In fact, it turns out that if f is a rational function, which is defined everywhere on the spectrum, in the sense that the poles of f are outside the spectrum, then the element f of a is also well defined, and we have this equality. Well, maybe this is also a nice exercise in commutative algebra. An exercise is to extend the polynomial spectral mapping theorem to rational functions. Oh. I had to erase that blackboard. Well, okay. I mean, anyway. So far we have seen that the notion of spectrum is purely algebraic. But the truth is that in the purely algebraic case, this notion is not very useful. But the situation changes if we apply this notion to functional analytic objects. So our next goal will be to introduce Banach algebras and to show that the spectrum of an element of a Banach algebra is always compact and non-empty. So to begin with, let's introduce normed algebras. So by definition, a normed algebra is an algebra A, is usual associative and all over the complex numbers. Together with the norm, together with a norm on A, such that the norm is compatible with the multiplication in the following sense. The norm of the product of two elements is less than or equal to the product of their norms. This property means that the norm is submultiplicative. And also, if A is unital, we also require that the norm of the identity element is 1. This is quite natural and quite useful for technical reasons. And finally, by definition, a Banach algebra is a complete normed algebra. Banach algebra is a complete normed algebra. Well, by the way, if we look again at this condition, then we can easily see, and this is a simple exercise for you, that the multiplication on a normed algebra is continuous. the multiplication on any normed algebra is continuous. Actually, this exercise is a special case of the continuity criterion for a bilinear operator between normed spaces. And this is one of the exercises in exercise sheet 4. And moreover, another exercise, which is not in the exercise sheet, but which is also quite useful, is to show that actually if we have an algebra equipped with a norm in such a way that the multiplication is continuous, then we can always rescale the norm, that is, multiply it by a suitable constant, in such a way that the new norm will be submultiplicative. So essentially, from a topological point of view, this condition is almost equivalent to the continuity of the multiplication. And moreover, if A is unital, we can always replace our norm by an equivalent norm such that this equality holds. Okay, now let's look at some examples of Banach algebras. Well, first of all, of course, we have a trivial example. The field of complex numbers, of course, is a Banach algebra. Example 2. If you take any set, if x is any set, then little L infinity of x, the algebra of bounded functions on x, is a Banach algebra. Well, indeed, we already know, or first of all, clearly it's an algebra under pointwise multiplication. Also, we already know that this is a Banach space, and it's elementary to show that the supremum norm is submultiplicative. So it's a Banach algebra. Example 3. Suppose now that X is a topological space. And let's look at the algebra of continuous bounded functions on X, CB of X. The algebra of continuous bounded functions. Well, we know that this is a closed subalgebra in L infinity of X. This is a closed subalgebra. But it's immediate that the closed subalgebra of a Banach algebra is also a Banach algebra. In particular, the algebra of continuous functions on a compact topological space is a Banach algebra. Example 4. Well, it's a little exercise, but the exercise is quite easy. If we take the algebra big L infinity of essentially bounded measurable functions on any measure space, X mu is a measure space, then L infinity of X mu is a Banach algebra. Well, indeed, we already know that it is a Banach space under the essential supremum norm. Also clear it's an algebra under pointwise multiplication. And it's a very simple exercise to show that the essential supremum norm is also submultiplicative. So it's a Banach algebra. Example 5, which is also a little exercise. Let's now look at the algebra of n times continuously differentiable functions on a closed interval AB. I claim that this is also a Banach algebra. Well, clearly it's an algebra, and we know that this is a Banach space under a canonical norm, which is defined to be the maximum of the supremum norms of the function and of its derivatives up to the nth order. But this a delicate point here is that this canonical norm is not submultiplicative. But this is a Banach algebra with respect to the following norm, which is equivalent to the original norm. So the new norm is given by the following formula. We take the supremum norm of the kth derivative and divide it by k factorial, and take the sum from 0 to n. And this norm is easily seen to be submultiplicative and equivalent to the original norm. And final example 6, which is probably the most important for us. Example 6. If X is a Banach space, then B of X, the algebra of bounded linear operators on X, is a Banach algebra. Well, indeed, we already know, we proved some time ago that this is a Banach space under the operator norm. And also we know that the operator norm is submultiplicative. So it's a Banach algebra. Okay, now we have the following important result, which describes some properties of the multiplicative group of a Banach algebra. So we have the following theorem. Suppose that A is a unital Banach algebra. Then we have the following results. First of all, result 1 states that if little a is an element in our algebra, and the norm of A is strictly less than 1, then the element 1 minus A is invertible. And we have an explicit formula for the inverse of this element, which is basically the geometric progression, the sum of the geometric progression. Part 2 states that the set of invertible elements, the multiplicative group of A, is an open subset of A. And finally, part 3, I claim that the inversion map, the map from A cross to itself, which takes each invertible element A to its inverse, is continuous. This is quite natural, but this is not in the definition of a Banach algebra. This is a property of a Banach algebra. I see that the Zoom conference has stopped. So I'll just restart it once again, and those of you who follow the Zoom conference can reconnect by the same link. Okay, so let's now prove this result. Well, part 1, we start with this series, and first of all we observe that the series is absolutely convergent. Well, indeed, the norm is submultiplicative. So we can estimate the norm of a to the power k by the kth power of the norm of a, by the submultiplicativity of the norm. But the norm of a is less than 1, and so this series converges. So we conclude that this series is absolutely convergent, but A is complete, and an absolutely convergent series in the Banach space converges. So this series converges in A. And let B denote the sum of this series. So we want to show that B is the inverse of 1 minus A. Well, to prove this, let's consider the sum from 0 to n. So also let Bn denote the sum from 0 to n of a to the power k. Then if we multiply y minus a by Bn on any side, the product is easily seen to be 1 minus a to the power n plus 1. It's a little calculation. So almost everything cancels, but only two terms survive, 1 and minus a to the power n plus 1. And since the norm of a is less than 1, and we have this estimate, this implies that the norm of, this element goes to 0, and so this element goes to 1. This goes to 1 as n goes to infinity. And this implies that 1 minus a multiplied by b equals b multiplied by 1 minus a, and this is 1. And this completes the proof of part 1. So this element is invertible, and the inverse is given by the following formula. Okay, now part 2, we have to show that the multiplicative group is open. Well, to prove this, we take an arbitrary invertible element, little a, and observe that the left multiplication map, LA, from A to itself, which takes each element B to AB, is a homomorphism of A onto itself. Well, indeed, it is continuous, it is bijective, and the inverse map is just the left multiplication by the inverse element, which is also continuous. So it's a homomorphism of A into itself, and let's also observe that this homomorphism takes the set of invertibles onto itself. Okay, now let's come back again to part 1. So part 1 means exactly that if we take the open unit ball centered at the identity, then this open unit ball consists entirely of invertible elements. So let now U denote the open unit ball centered at the identity. So part 1 implies that this ball is contained in the multiplicative group. And after we apply the multiplication LA, we obtain a subset which is also contained in the multiplicative group. But on the other hand, this set, LA of U, is a neighborhood of A. It contains A because U contains the identity, and it is open because U is open, and LA is a homeomorphism. A homeomorphism takes open sets to open sets. And that's it. So we have shown that each point in a cross belongs to a cross together with a suitable neighborhood. So a cross is open. Okay, now part 3, we have to show that the inversion map is continuous. First of all, let's show that this map is continuous at the identity of the algebra. So we take an element, little a, which is close enough to the identity. It is 1 minus a, then 1 minus a is less than 1. And let b denote 1 minus a. Well, b is 1 minus a, so a is 1 minus b. Now the norm of b is less than 1, and part 1 implies that b is invertible. B is invertible. Well, let's calculate the inverse of this element. So what we want to do is to compare, to estimate the difference between 1 and a inverse. Oh, sorry, not b. B is less than 1, and a is 1 minus b. So we apply part 1 to b, and we conclude that a is invertible. A is invertible. Well, a is invertible, and so we now calculate the difference between 1 minus a inverse. So basically what we want to do is to show that if this is small, then this is also small. This will mean that our map is continuous at the identity. Okay, now what is this? A inverse is 1, a is 1 minus b. A is 1 minus b. And we have a concrete explicit formula for this element from part 1, the geometric progression. And when we, well, maybe let's write it in the following equivalent form. So part 1 implies now that this is the sum from 1 to infinity of b to the power k. So the identity is b to the power 0, and as a result we have the sum from 1 to infinity. And this term can be estimated as follows. Here we use the triangle inequality and the assumption that the norm is submultiplicative. And this is a formula which you probably know from your secondary school, the sum of the geometric progression. Looks like this. Now, if a goes to 0, if a goes to 1, then b goes to 0. So this number goes to 0, and this number goes to 1. So everything goes to 0 as a goes to 1. And this implies that our map is continuous at the identity. Hence, the map which takes a to a inverse is continuous at the identity. Now, to complete the proof, we just use the following simple lemma, which is a simple exercise for you. Suppose that we have an arbitrary group, G is a group, equipped with a topology. Such that, first of all, the multiplication is continuous. And such that the inversion map is continuous at the identity. I claim that the inversion map is continuous everywhere on G. So this is more or less standard trick based on translations. So the continuity of the multiplication together with the continuity of this map at the identity actually imply that this map is continuous everywhere. So to complete the proof of our theorem, we simply apply this lemma to the multiplicative group of our Banach algebra. And we see that the inversion map is continuous. Okay, so this is theorem 1 about Banach algebras. Let's now apply this result. Well, first of all, we have a useful and nice corollary. First of all, let's give a definition. If A is any algebra, then a character of A is an algebra homomorphism. Say chi from A to the complex numbers. And let's observe, it's a simple exercise again, that if A is unital, and chi is a non-zero character, then it is unital. Well, actually, this is not an exercise, it's a simple observation, because if chi is non-zero, then it is surjective, because it's a linear map, it's a linear functional. So a non-zero linear functional is surjective, and it's almost obvious that a surjective homomorphism between unital algebras is automatically unital. So we now have the following corollary from theorem 1. Suppose that A is a unital Banach algebra, and chi is a character of A. And I claim that chi is continuous automatically, and the norm of chi is less than or equal to 1. This corollary illustrates a rather general phenomenon which is quite typical for Banach algebras. The phenomenon is called automatic continuity. So it turns out that quite often the continuity of a certain map automatically follows from its algebraic properties. And there is a rather advanced theory of automatic continuity for Banach algebras, which studies automatic continuity of homomorphisms, derivations, cocycles, and some other maps related to Banach algebras. There are several monographs on this subject and numerous research papers. So this is the simplest example of automatic continuity. Each character of a unital Banach algebra is automatically continuous. And the proof easily follows from our previous result. Namely, assume that this is not the case. Assume that chi is either discontinuous or equivalently unbounded, or is bounded, but the norm of chi is strictly greater than 1. In both cases, we can find an element. There is an element B in our algebra such that the absolute value of chi of B is strictly bigger than the norm of B. This follows from the definition of a norm of a linear operator. So if we now divide B by the norm of B, we get an element little a such that the norm of a is less than 1, but chi of a is exactly 1. The norm of a is less than 1, and part 1 of theorem 1 implies that 1 minus a is invertible. Chi is a character. Without loss of generality, we may assume that chi is unital. Because this exercise shows that chi is either unital or is 0. But if chi is 0, then there is nothing to prove. So we may assume that chi is unital. And the unital homomorphism takes invertibles to invertibles. So this element is invertible, so it is a non-zero complex number. But what is this? This is 1 minus chi of a. And 1 minus chi of a is 0. And this is a contradiction. And this contradiction shows that chi is actually bounded and the norm of chi is less than or equal to 1. Okay, let's now apply this result, I mean theorem 1, to the study of spectrum in Banach algebras. So let me recall once again that our main result will state that the spectrum is always compact and non-empty. So let's start with the compactness. Theorem 2. Suppose that A is a unital Banach algebra, and that little a is an element of our algebra. Then I claim that the spectrum of A is compact, and moreover that for each element lambda in the spectrum, we have the following inequality. The absolute value of lambda is less than or equal to the norm of A. Well, it will be more convenient for us to start with the second part of this theorem. Well, let's take any complex number whose absolute value is bigger than the norm of A. Then we have to show that this number is not in the spectrum. Well, we divide by lambda, and we see that the norm of lambda inverse A is less than 1. So theorem 1 implies that 1 minus lambda inverse A is invertible. And if we multiply now by minus lambda, we conclude that A minus lambda is invertible. Or equivalently, this means that lambda is not in the spectrum. And this completes the proof of part 2. Now to prove part 1, it suffices to show that the spectrum is closed. In the complex plane. Well, indeed, part 2 already implies that the spectrum is bounded, and the subset of the complex plane is compact, even only if it is bounded and closed. Well, why is it closed? To show that it's closed, we consider the following function, as denoted by phi, from the complex plane to A. This function is given by the following simple formula. Phi of lambda is A minus lambda. Then, by the definition of the spectrum, we see that the complement of the spectrum on the complex plane is precisely the set of those lambda for which this element is invertible. So this is the preimage of the multiplicative group of A under phi. But phi is obviously continuous, and theorem 1 implies that this set is open. A cross is open in A, and since the preimage of an open set is open, we conclude that this set is open on the complex plane. And so this means that the spectrum is closed. Okay, so this completes the proof of Theorem 2. Now our next goal will be to show that the spectrum is non-empty. Before we can prove this result, let's introduce the following definition. We define the resolvent function, of an element of our algebra as follows. This is the function Ra, which is defined on the complement of the spectrum. It takes the complement of the spectrum to our algebra, and this function is given by the following formula. A minus lambda inverse. In Russian, резольвентная функция. First of all, let's prove that this function is continuous and vanishes at infinity. The resultant function is continuous and vanishes at infinity. Well, first of all, the continuity is immediate from theorem 1. Continuity follows from theorem 1 because the inversion map is continuous. Now let's show that it vanishes at infinity. Well, this is actually a little calculation. So A minus lambda inverse. What is this? So we take lambda out of here. So we get the absolute value of lambda inverse multiplied by the norm of 1 minus lambda inverse A, and we should take the inverse of this element. Now, clearly this goes to 0 as lambda goes to infinity. Lambda inverse also goes to 0, so the expression at brackets goes to 1. And again, we use the fact that the inversion is continuous, and we conclude that this element also goes to 1. This goes to 1. So the product goes to 0 as lambda goes to infinity. Okay. So the resolvent function is continuous and vanishes at infinity. Our next result will show that this function is not only continuous, but is also holomorphic in the following sense. So we give the following definition. Suppose that U is an open subset of the complex plane, and X is a Banach space. And suppose that we have a function, phi, from U to X. we say that phi is holomorphic. Well, essentially, the definition is exactly the same as in the case of complex valued functions. It is holomorphic if and only if for each point in U, for each z in U, there exists the following limit: phi of w minus phi of z over w minus z. The limit as w goes to z. And this is an element of x. And it's natural to call this limit the derivative of phi at z. This is just a notation for this limit. So phi is holomorphic if it is differentiable in the complex analytic sense. Let's now observe that each holomorphic function from U to x generates a whole family of complex valued holomorphic functions. Let's observe that if phi is a holomorphic function from U to x, then for each bounded linear functional f on x, if we take the composition of phi and f, this is a complex valued function on U, and this function will be holomorphic in the usual sense. This function is holomorphic. And moreover, the derivative of this function at every point, little z, is just f evaluated at the derivative of phi at z. This is almost immediate from the definition, because if we apply f to here, so the continuity of f implies that we can interchange f and the limit, and also we can put f here and here by linearity, and we get the derivative of the composition of f and phi. Okay, now we have the following simple algebraic result, which is the so-called Hilbert's identity. Hilbert's identity. This is the identity of the following form: r of lambda minus r of mu equals lambda minus mu multiplied by r of lambda, r of mu. And this holds for all points lambda and mu where this expression is defined. This lambda and mu are complex numbers which are not in the spectrum array. The proof is an elementary algebraic exercise, just a little calculation. Basically, to prove this formula, you just multiply both sides by a minus lambda and by a minus mu. This will be an equivalent formula because both elements are invertible, but it will be very easy to check that the new formula is indeed true. Well, now as a corollary of the previous propositions, we conclude that the resultant function is holomorphic everywhere on its domain, that is on the complement of the spectrum. And moreover, the derivative of this function is equal to r of lambda squared. Well, indeed, to prove this result, we simply divide both parts of Hilbert's identity by lambda minus mu, and let mu go to lambda. Then the right-hand side will be this product, which goes to r of lambda squared by the continuity of the resolvent function, and by the continuity of the multiplication in our algebra. Okay, now we can easily prove the fact that the spectrum is non-empty. Theorem 3, suppose that A is a non-zero unital Banach algebra. Then the spectrum of each element in A is non-empty. The spectrum is non-empty. The proof is a nice application of complex analysis. Let's assume the converse. Assume that the spectrum is empty. And we'll take any bounded linear functional f on A. And let's compose f and the resolvent function. Well, now it is defined everywhere on the complex plane because the spectrum is empty. This function is holomorphic. It's holomorphic. And by one of our previous propositions, it vanishes at infinity. Well, a continuous function which vanishes at infinity is obviously bounded. It's bounded on the complex plane. And now recall the classical Liouville theorem, Liouville's theorem, which states that a bounded entire function, that is a bounded function which is holomorphic everywhere on the complex plane, is a constant. But a constant which vanishes at infinity is identically zero. And this happens for each lambda on the complex plane and for each bounded linear functional f on A. And now we look at this element, Ra of lambda. So this is an element in our algebra, and it has the property that all bounded linear functionals vanish at this element. Now, the Hahn-Banach theorem implies that this element is actually zero. But on the other hand, this element is obviously invertible. So 0 is invertible. This can happen only if the algebra is 0. And this completes the proof. So we see that the spectrum of any element of a unital Banach algebra is always compact and non-empty. Well, if you don't mind, I just want to state a very easy but a very nice corollary, just a couple of minutes. The so-called Gelfand-Mazur theorem. Gelfand-Mazur theorem. Suppose that A is a Banach division algebra. Which means that A is a non-zero unital Banach algebra. A non-zero Banach algebra such that all non-zero elements are invertible. Sometimes such algebras are called skew fields. It's almost a field, but like a field, but it is not necessarily commutative. So A is a Banach division algebra. How many well, we know one of them, the complex numbers. The theorem states that this is the only Banach division algebra. And the proof is very easy. We take an arbitrary element in our algebra. We know that the spectrum is non-empty. We know that the spectrum is non-empty. So we look at the element A minus lambda. This element is not invertible. But by assumption, all non-zero elements are invertible, and so this element is 0. That is, A is just lambda 1. So we see that A is one-dimensional over the complex numbers and is spanned by the identity. So it is isomorphic to the complex numbers. Just a few words in conclusion about the history of this result, because the history is quite interesting. First of all, the Gelfand-Mazur theorem also has a real version, a version of the real numbers, which states that if you have a real Banach division algebra, then there are only 3 possibilities. It is either the real numbers, or the complex numbers, or the quaternions. This result is, by the way, is much more involved. The proof is much more involved than in the complex case. And this result generalizes the classical Frobenius theorem, which states that if you have a finite dimensional real division algebra, then it is either real numbers or the complex numbers or the quaternions. So it extends the Frobenius theorem to the infinite dimensional setting. And the history is as follows. This result was first announced by Mazur. Stanisław Mazur was a great Polish mathematician, and this result was announced by Stanisław Mazur at the end of the 1930s. And it was stated already over the real numbers. But for some strange reason, Mazur submitted his paper to the French journal Compactness, which is known to publish only brief communications. And the answer that Mazur received from the editors was that, well, your paper is too long for our journal. So if you want to publish it in our journal, then please reduce the size of the paper. And Mazur reduced the size of the paper. He just threw away all the proofs. So the paper was published, but without the proofs. And the first published proof of the Gelfand-Mazur theorem was due to Gelfand. It was published in 1941, but it was only over the complex numbers. And the first published proof of the original Mazur theorem about Banach division algebras over the real numbers was published only in 1960 in Rickard's book on Banach algebras. Okay, so that's all for today. At the next lecture, we also discuss one more general concept from Banach algebra theory, namely the concept of spectral radius. And then we apply our results about Banach algebra, so we begin to discuss spectra of bounded linear operators. So we will see that the spectrum of bounded linear operators can be naturally divided into several disjoint parts, and we will see how to calculate the spectrum. Thank you.